No, one's aluminum and one's not. Put them in your hand and throw the slider.
Okay.
It's the aluminum.
All right. Whoa, what happened there? Here we go. Okay. That's better. So we are looking at bonding here. There we go. That should show up better. All right, so different types of chemical bonds. We talk about ionic and covalent, and then we have different types of metallic alloys that we will also cover in this section. So remember we talked about electronegativity when we were talking about periodic trends in our last chapter. And we said that electronegativity measured the ability of the atom to attract shared electrons. Does this look right for your notes? Okay, all right. So this, of course, can be explained by Coulomb's law. So if we have something that's like pulling on an electron really strong, it's going to come over, okay? Kind of like red rover, when you're talking about ionic bonding, okay? If the electronegativity difference is vast, like really large, it's going to end up pulling that electron over completely or essentially ripping it off of the other ion or other atom to make an ion. Okay. Remember, cations are positively charged. Meow. Okay. Those tend to be your metals. And then we have your non-metals that tend to be negatively charged. Okay. Those are called anions. And as that electronegativity difference decreases, you will end up having a covalent bond. Okay. You can still have ionic character in a covalent bond, particularly when something is very polar. So it's all a continuum. It's a spectrum. Okay. Remember, this is increasing electronegativity. Oh, come on. Go back. There we go. Increasing electronegativity as we go across here, but that really doesn't apply to these guys. Why? And right, their valence shells are full, so they don't need to get rid of or attract another electron. They're already kind of satisfied. Okay. Now I know that I use a lot of personification in the notes. Don't do that. Don't personify atoms in your answers. Okay. When you get into the AP exam, I try to do those analogies to get you to help like have connections kind of in your brain with the concepts, but they're not actually real people and they don't have feelings and yeah. Anyway. No. So this is our greatest electronegativity. They give that a number 4. This is 3.5, 3, 2.5, 2, and then hydrogen is 2.1. Okay. You don't necessarily need to know these. You just need to know kind of the trend of what's happening with them. As you move across here down to this area, electronegativity is going to get less and less. Make sense? You looked toward this electronegativity difference to give you a clue or a hint as to what type of bonding it's going to be. Okay. Do I talk about that? Yeah, I do right there. Okay. I wanted to mention something, but I see that I'm going to, so I don't want to get ahead of myself. All right. Like I said, fluorine is the most electronegative. It has a very small radius. So that's a small amount of electron shielding. There's not a lot of distance between the nucleus and those outer electrons. That's what that electron shielding means. Okay. So that's going to result in a strong pull on electrons. Now, we can end up using these electronegativity differences to tell us what type of bond it's going to be. These are the 3 bonds that we're going to be talking about. Okay. Again, you can have a polar bond that has ionic character. And what we mean by ionic character is like a high melting point, for example. Okay. Ionic compounds, I don't have a flame in the back of my room that will melt ionic compounds. I can't even get them into a liquid form. Okay. The temperatures are stupid high on those. All right. When we're looking at this, if we have non-polar bonding, that's going to be an equal sharing of electrons. Polar bonding is an unequal, but it's still shared. And then ionic, you're going to transfer. Okay. So here they try to give you an image of what that looks like. A and B are going to be equal. Now, there are some people that actually feel that the only true non-polar bond is one that is the diatomic elements, where the electronegativity is equal. Okay. But in here, and typically for AP, the cutoff is around 0.4 or 0.5 for the differences. So for example, if you had CH4, your electronegativity difference would be 2.1 for your hydrogen minus 2. What did I have written on here? For carbon, 2.5. 2.5. So that would be a 0.4 difference. That's going to be a non-polar bond then. Okay. I know this is negative. It's okay. It doesn't matter because it's absolute value. So just let it go.
Absolute value.
Just let it go. Channel your inner Elsa and let it go. If we have something like HF, hydrofluoric acid, then this would be, what is that? 2.2, so it's a 1.9 electronegativity difference. Okay, very polar, very, very polar. Almost to the point where it's ionic. Okay. Now, why isn't it shared? Well, they're both non-metals, so then they kind of consider it still to be a covalent bond because they're both non-metals. But the electronegativity difference definitely puts it into the ionic character. Okay. Fluorine is such an electron hog. It's not even funny. Like I said, this is all a continuum here. Whoops. Shoot, come on. This is all a continuum here as you move through. So type of bond as you move through different amounts. Good? All right. There we go. So HH, or any diatomic element, your Brinkelhoffs, any of your Brinkelhoffs, those are going to be non-polar covalent bonds. HBr, there's some difference there, but it's still considered a covalent bond. And then when you get to ionic bonds, they have a large difference in values. The electrons aren't shared, they're transferred. They just give it away. It's a give and take. It's kind of like you and your parents. Parents just give, and you guys just take. And do it as much and as often as you can because it won't last forever. The gravy train gets cut off at some point. All right, ionic bonding characteristics. And they will sometimes give you characteristics of a substance and then ask you to say what you think it is. They won't tell you what it is. They won't say, this is sodium chloride. They'll say, this unknown... What the heck? What happened there?
Your boy absolutely loves and adores you, Libby, and just wants to tell you Happy Monday.
Oh my God. I think it's because I hit this wire. There. Okay. Oy. Goodness. Where was my train of thought? Oh, yeah. So they will sometimes tell you this unknown compound has these characteristics, and then you have to be able to identify, is it ionic or covalent based on that. Okay, so if they were to do this and they said it forms crystals, forms a lattice. Remember, a lattice is kind of like that scaffold that forms. Okay, and the basic unit of this is a formula unit. So if you broke it down and you had the tiniest like amount that would still be combined as a compound, that would be called a formula unit. Just like an element, the tiniest part is. Would you like to buy a vowel? Atom. There you go. Okay.
I thought it was rhetorical. It's hard to tell sometimes.
Okay. So high melting and boiling point. So like I said, we're not going to get a flame in my room that's going to be able to be capable of melting any of this stuff. They're hard. They're brittle. Think of table salt. They conduct electricity. Now, this is important. They don't conduct electricity when they're a solid, like a metal would. They conduct electricity when they're dissolved. Why? Why would that conduct electricity when it's dissolved? What happens to these compounds when they're dissolved? I have a solid. And I plunk that guy down into the water. What's going to happen to him?
They'll break up.
Yep, it's going to break up into ions. So you're going to have, over here, we've got water. You're going to have a chlorine ion. You're going to have a sodium ion. And guess what can happen now? They can conduct electricity because they're charged particles. As a solid, they can't do this. But as a liquid, they can. So they're able to move that electrical charge through there. As opposed to a metal, where a metal can do that either in its solid form or in its molten form. Covalent compounds can't do either. Okay? So water, actually pure, 100% water, cannot conduct electricity. Because it doesn't have any charges on it. Now you tell me, Lippy, they say not to mix electricity and water. Well, what was my caveat when I said that? Absolutely pure water. Is water that you deal with on a daily basis absolutely pure? No. You mix it in, you drop it on the basement floor, I can guarantee you that water is not pure anymore. Okay? So now you're standing in stuff that's capable of connecting and moving charges around your dead. Okay? But technically, absolutely pure water is not going to conduct electricity. All right. These can also make good insulators as a solid. All right. Metallic bonding. Metallic bonding is going to occur between metal ions. With this, we tend to have a sea of electrons. So the electrons are what they call delocalized. They're able to move from one atom to another. So these are a sea of freely moving negative electrons. Okay? Properties of metals and metallic substances. They are shiny. That means they also use the word luster for that. Luster means shiny. They are malleable. What does malleable mean?
Like you can bend it,
Shaped.
Right. You can, pound it out into thin sheets like foil, aluminum foil. Ductile. What does that mean?
So that you can draw it into a wire.
Yep. You can heat it up and then pull it and draw it out into thin wires.
It's such a weirdly specific term.
I know, isn't it? But I mean, malleability, if you think about that, you can kind of have the image of the blacksmith where they heat it up and now it's glowing, and then they take the hammer and they pound it out and they're able to kind of, make it into any shape. It's kind of cool. They conduct heat and electricity even in their solid forms. Metallic oxides are basic and ionic. So that just means that if you have like Na2O, that's going to be basic if you put it in water. And we'll get into that later on this year. Don't want to touch that one yet. And then they're also ionic compounds because of the electronegativity differences. And then they lose electrons to form cations. So all metals tend to lose electrons. And that's why you have the, last year I gave you a periodic table and it had the pluses on it for different things. You don't have to know, for example, that copper is a +1 or a +2. But you need to be able to look at a substance like this and be able to tell that copper here in this state has what oxidation number?
+2.
It's a +2, because if this is a -2, which it is all day long, except when it's in a peroxide, we'll get into that one later too, because we always have exceptions. But if this is in a 1-to-1 ratio and this is a -2, this has to be a +2. Okay? If I did this, though, now it's a +1, because I would need 2 of these for every one of those. Okay? And remember, cations are positively charged ions. All right. Properties of nonpolar and covalent molecules. They don't shine. They're dull. They're brittle. They're hard. Sometimes they're soft. They're poor conductors. So if we put these in a liquid, some of them will conduct electricity, especially those covalent compounds that are getting closer to that ionic compound electronegativity difference. They'll start to conduct a little bit of electricity. Their nonmetallic oxides are acidic and covalent. And again, we will get into why that is the case later on in the course. And then they're going to form anions by taking in electrons and becoming more negative. All right, place the following bonds in increasing polarity. So these are all with carbon. And essentially what I'm doing here is I'm looking at what's at the end and the differences there, or in this case, the beginning. So increasing polarity, which one is going to have the highest polarity?
CC. Carbon chloride.
This guy right here might surprise us. Yeah. So this guy right here, what do you notice about it that's different from all the rest of these?
Calcium isn't in the second
Right.
P or second S.
So, well, not only that, but it's a metal, right? The rest of these are all nonmetals. What do we know about the electronegativity difference between a metal and a nonmetal? It's very large. Okay, that's why you form ionic compounds. So this guy is going to be way over here. I'm going to go ahead and place him. Now, the rest of these are all nonmetal. That's what we have left. So now we're going to look at the electronegativity difference here. What's going to have the greatest electronegativity difference from these? Yep, so I'm going to put him next. Okay, so I've got this one taken care of. I have this one taken care of. Which one is going to be way over here, the most non-polar? Carbon, because the electronegativity difference, without knowing the values, we know that the electronegativity difference of that guy is 0. Okay, so we got rid of him. Now we have to figure out between these two. Which one is more electronegative, oxygen or hydrogen? Oxygen. So it's going to go here, and CH is going to go here. And now we've got them ranked. All right, we do. Take a minute and see if you can classify these things as nonpolar covalent. Well, they gave you a chart there, right?
Yeah.
Didn't they? Yeah.
Yeah.
They gave you guys a chart. I just didn't give myself one here. Take a minute, see if you can classify these.
Is the one at the end there just aluminum?
Huh?
Is the one at the end just aluminum?
Yep. Yep. Anybody need more time? Okay. Good. More time? Okay. So this one should be easy. Anytime you see a diatomic, you know automatically electronegativity difference in a diatomic is 0. So this has to be a nonpolar covalent. So you should have that in that box. Okay. This is a metal and a non-metal. Ionic. Again, metal, non-metal. Non-metal, non-metal. Let's see here. Electronegativity difference here is 3.5 and 3.0. So the difference is 0.5. This is right on that line. They would never give you one that's right on the line. Okay. So you could either go non-polar covalent, but I would probably go polar covalent, just to be on the safe side, because it's probably going to have some of that polar covalent character to it, because it's right there. It's just butt right up against the line. All right, these are two metals, so what are they going to be? Metallic. This is a non-metal, non-metal. You didn't have the electronegativity difference for chlorine. I think, did I write down what chlorine was on here? Chlorine is right below, so I think it's around 3. And NO is, and that's nitrogen is 3 as well. So this is like around 3, maybe like 3, 4, something like that. So this is going to be nonpolar. Oh, it hates me.
It's just saying happy Monday.
Yeah, happy Monday. We already went over this one earlier today. So this is right on the edge. I would probably go nonpolar covalent here. And then AL is just metallic. Everybody happy with that?
Mm-hmm.
Making sense of it?
Mm-hmm.
Okay. So you got the you do for homework tonight on that. And now we're going to talk about intramolecular force and potential energy. Not intermolecular force, that's unit 3. This is intra. What does intra mean when you have the prefix intra? Right, it's within the molecule, within the thing, okay? So the internet or interstate goes between two things. This is within that thing. So Highway 26 would be at intrastate because it's within Wisconsin. It doesn't go to Illinois. It doesn't go to other states. So it's intrastate. It stays within this state. Now, of course, they just call it a highway, but, you know, if we want to get fancy about it. All right. Covalent compounds are bonds between two nonmetals when they share electrons. They can be either polar when it is an unequal sharing, or they can be nonpolar when it's an equal sharing. Covalent bonds then can be single, double, or triple bonds, or an average of those where there is resonance. And we've talked about resonance back in chem land, back in regular chem and honors chem. I will be talking more about that as we move through here the next part of this week or so. Covalent bonds then occur at the lowest energy state. This happens when the attraction between the nuclei is greatest for the shared electrons, but the repulsions are minimized. If the atoms are too close together, then you're going to get repulsion of your nuclei. So there's kind of a sweet spot. Okay, so we've got some graphs here that'll kind of show that. Okay. So out here, remember Coulomb's law, we have a force of attraction or repulsion, and we have distance. If the distance is too great, you're not going to have that attraction happen and form a molecule. If that distance is too close, then the nuclei are going to get too close to each other and it's going to push it apart. So like I said, there's just a sweet spot here where the repulsive forces are minimized and the attractive forces are maximized. Okay. At that point, you can also look at the potential energy. When this forms, it gives off energy. Okay. So this is for the HH. So our bond length, we can look at bond length here. If they're too far apart, it's not going to work. It's like the two magnets. If they're too far apart, they're not going to click together. If they're too close, then the nucleus is going to shove them apart. It just hates me. All right, so bond energy is the energy required when breaking a bond or the energy released when it's formed. The magnitude is the same, but the sign is different. And we will actually get into using the values for these things are called enthalpies. We'll get into that. I believe it's unit 6. That's where we get into it. So we'll actually come back to these tables when we get into this, and we'll actually do calculations with these. Okay? But that's not until January. Larger radii then increase the bond length. Longer bond length, less energy. So you won't have had as much released. It's January. It's going to be cold then. I won't be wearing short sleeves or flip-flops. More electrons involved. the greater the attraction, and the bond length is decreased. So what they're saying with that is when you have let's see, we've got a CC bond here, and we're looking at the bond length. No, that's enthalpy. It's not the enthalpy and the bond length are both indicators of strength. So we're just going to look at enthalpies here because I got a table with these. So you can see if I just have one bond, that's 348. If I have multiple bonds, though, 614, 839. So the potential energy increases as we increase those bonds. Nitrogen's also given here, so 163 for the enthalpy, and then here, nitrogen, double, and then triple bonded. Okay. Lattice energy then, you will not have to calculate this at any point. That's the energy that's used to separate compounds. It's defined as the change in energy when they go into a gaseous ion state. And then combining ions will actually release energy. So lattice energy can be represented with modifications to Coulomb's law, where you're looking at radius here instead of just distance. You're looking at the radius of the ions. Again, you're not going to have to calculate this. It's just simply looking at it. All right, we have bond energy here for a double carbon bond. We know that that is 614. Bond length is 1.34. They want us to sketch a CC bond, a single bond, on this graph and include a key. So blue for me, or purple, I'm going to, whatever, blue. Blue is going to be CC. And red is going to be CC. Okay. All right. So, do we expect our new CC bond, single bond, to have more potential energy or less potential energy? It's going to be up here, though, isn't it? It's going to be somewhere here. So it's more. Yep. Okay. Do we expect the length, the bond length, to be greater here or here? Single bond or double bond? Single bond. So our length is going to be on this side of this. So it's going to be somewhere. So if we were to draw this, it would look something like this. I'm going to go one more step. Now I want to talk about a triple bond. What would you expect to happen there?
More energy and further to the left.
Okay, less energy, but further to the left. Yep, so it's going to be over here. It's going to dip down here, and then it's going to come up. And they will ask you to superimpose these things, or they will give you a graph like this and then ask you which one of these would represent the triple bond. Yeah.
How do you know where it dips down?
So the more bonds it has, the less potential energy it's going to end up having. So they have to give you a frame of reference. So like I said, they gave us this blue one for the double bond. So we know that the triple bond is going to be down here further. And the single bond would be up here. And the triple bond would be closer together because it's like three things pulling on it, holding it together. It's going to be closer in. The bond length is going to be less. All right, one way to identify an unknown substance is to measure the bond energy. So we have HX, HY, and HZ. They're analyzed. The following graph was created. We know that HI, HCl, and HBr were tested. They want you to tell them which one matches which. So you're trying to figure out which one of these is these compounds. You're identifying them. Well, what do we know about those three compounds on the periodic table? What's different between the three? What's different between HI, HCl, and HBr?
Just how far down they are.
The anions, right? Okay. So Cl is here, Br is here, and I is here. Which one of these is going to have the greatest bond length? The HCl or HI?
HI because it's a metal and a non-metal.
No, they're both nonmetals.
HI because it's like greater distance.
The radius, yep. So HI is like this. HCl is like that, right? Layers of the onion.
Mm-hmm.
Okay. So bond length between these two radii is going to be less than the bond length between these two. Okay. So if we just look at the internuclear distance, this guy right here, HZ, is going to be the furthest apart. So that has to be HI. This is going to be the closest. So it would be HCl, which leaves HBr. Good? Makes sense? All right. So you have some cobwebs to knock off tonight. And 2-1 and 2-2 are due tomorrow. And then we'll start singing because that just gets ugly.